Hello, good afternoon, good morning, everybody. This is Edwin van der Leden from sunny Rotterdam in the Netherlands. Welcome to this YouTube live stream. It's a coffee break with Eddyfi Technologies. I got a cup. I hope you got one as well. To start with, I hope that everybody is keeping safe and healthy, as well as your families. And today I have a presentation for you during this coffee break, which is about remote crawlers, remote inspections using for tank inspections, vessel inspection, and pipe inspections. I have some examples and a presentation and some video that I would like to show you. If you have any questions on the presentation, then please keep your questions to the end of the video. You can type them in the chat, and will be answering them afterwards. But I have understood that you need a Gmail account to actually make sure that you can enter those questions. This session is also recorded, and it will be available on the Eddyfi website on the on-demand section. So be sure to check in later if you're interested. Let's get started. Like I said, I have a presentation today which is about remote inspections. And I want to give you an example of basically three types of inspections. One is for tanks using a Scorpion 2. One is for vessels with an RMS phased array system. And one is a project we've done with for a pipe inspection, long lengths of pipe with an Nocturne robot and R-Scan UT. Quite interesting. So like I said, we're going to use the Scorpion 2 product for tank inspections and show some examples. The RMS phased array, very cool and recently launched product that will allow you to do inspections with phased array on raster scanners, and then in a Nocturne robot. I'm going to show you that as well. So let's start with the Scorpion 2. Now, if you look at tanks worldwide, and there are many tank farms and literally thousands of tanks around the world, they all suffer from degradation, also due to aging and as well as the product that's in it. If a tank fails, then we have tremendous consequences and even loss of life. I think we saw a very recent example in Houston about a year ago. Great fires, which we obviously want to avoid. Then what we also see is the safety regulations are increasing worldwide, right? So more countries are introducing more strict regulations on tank inspections. And in many cases, this is now mandatory by government regulations. So this will be something to have a look at in the future as well. So what do we see with tanks? Which we see a lot of types of different corrosion, right? It depends on what is in that tank and how that erosion or corrosion actually evolves. What we see quite a lot is fluid level interface corrosion, chemical reactions where we have catalysts with product water and oxygen, creating a bad environment for the metallic surroundings. Also, microbiotic corrosion we see a lot. It depends on what's inside the tank, and also environmental conditions like wind, rain, cold weather, sunshine, condensation. One side of the tank is hot and the other side stays cooler. This is all affects the integrity of the tank. So in the bottom here, you see some examples of defects that we found, mainly tank bottoms, but you can also see them in shells. And then in the top, you see people, kind of interested in what's going on at the floor. But what struck me when I looked at this picture and I look at it closely is actually is this. If you zoom in on the wall, you can actually see the deterioration of that tank wall. So if we compare that to like the first meter and a half, almost that tank wall is unaffected. And again, if we zoom in, you can see there's quite substantial damage being done to that tank shell. If we look at traditional inspections of tank shells, then we see a lot of general purpose UT crawlers being used. Sometimes bolted together, or sometimes it's from standard products combined with UT solutions. All work great, already an improvement to what we were doing before, but still they have a lot of limitations. Still, we see a lot of visual inspections and UT spot checking, in many cases done with rope access and scaffolding. And if we go back to that picture where we just show that very local attack of that shell, then you can imagine that the probability of detection of that when you do like a UT spot check is quite low. Also, you would not recognize any corrosion patterns if they're there, and also there's no data recording if you just do simple UT spot checks. Having said that, then of course, something that we have to take into consideration is the HSE issues as well, right? If you build scaffolding, if you're hanging out on a rope on the side of a tank, then there are fall hazards. If you have to go in, there is entry of confined spaces, exposure to chemicals. So a lot of reasons why we want to limit the amount of having people actually physically accessing the tank shell. So what we developed in Eddyfi is a very nice crawler. It's a scanline inspection crawler. It creates a nice B-scan profile. And the nice thing is it can take measurements while the asset is in production, right? It does not have to go out of production. There's no need for rope access or scaffolding as long as the tank shell is ferromagnetic. The magnetic wheels on the Scorpion will actually allow the Scorpion to actually climb and make the measurement as it drives. So it's not a check. It creates a complete scan line over that whole tank. So a big advantage there, and I'll show you in latest slides why that is. Also, this tank is designed to measure at actually quite high speeds of 180 millimeters per second, allowing you to do tank shell scan lines very rapidly. Also, if you compare this to other UT technology, then we don't need a separate coupling mechanism. So no water, no extra coupling. What we have is a little oil container which wettens a wheel probe, which we call the DCP, as it moves along the surface. And DCP stands for dry coupled probe. And of course, we have data recording. So we record all the measurements while we drive that unit up a tank shell or tank roof. Look at it from a technical perspective. We're using a 5 megahertz dual element probe, but we've also recently launched a 2.5 and a 10 meg probe as well. So if you have thinner materials, thicker materials, we have the probe that actually fits the needs for your job. Like I said, variable speeds up to 180 millimeters per second or 7 inches per second. It's battery operated with a lifetime of 4 hours per battery. And both the crawler as well as the data acquisition unit both have their own battery supplies. That means that we're not carrying any power over the umbilical. The unit will have its own battery capacity. We have a very specially designed active probe head, which you can see here as well. I'll have a live demonstration a little bit later as well, which will allow that probe to be lifted and contracted or pushed against the surface when we're making measurement, and retracted when we're actually steering the unit, also making sure that we have maximum lifetime out of the probe wheel. And then this probe is stabilized, so there's a set of levers there which will balance that signal, making sure that we have a very smooth backwall signals and very precise measurements. Also, this unit is steerable 360 degrees, as we can see on the little picture here, and we have a standard umbilical of up to 50 meters. You can do a tank inspection of a large tanks and still have enough standoff, so you can actually see that crawler climbing up a tank. Now, what makes the difference between our product, the Scorpion 2, and what we were doing with other products, right? This is specifically designed for tanking, for measuring tank shells. Why? We have something built in which is called tracking and floating gauge, and I will show you the difference in a minute. The floating gauge is basically for compensating coupling variations, while the tracking gauge is actually to track whether there's a change in wall thickness. And we have automatic gain control, which with a push of a button, we can automatically change that gain to be 80% screen height, as we UT people would like to see that for precise measurements. So it will allow you to create very precise measurements on the varying circumstances as you drive up. You know, coating changes might change, the coupling changes might change, the material thickness change. So all this will automatically be adapted for with the special features that we have in the Scorpion 2 that you will not find on any other product. So if we look at the fixed gate, for instance, what we can see, if we have a fixed gate, for instance, you know, you can see that the echo, the wall thickness is changing, the echoes are changing, but my gate is fixed, meaning that I don't have a correct reading on my second backward echo, which will make it very hard to actually use that signal for interpretation. If we then go have a look at tracking gate, we can see that that gate is automatically tracking excuse me, the material thickness as it changes, and it will automatically adapt to whatever wall thickness it is currently measuring. We all know that tank shells on the bottom are quite thick, on the top they're quite thin, so this gate will actually follow the wall thickness. The reason why that is important, because we have designed a crawler which can run at 180 millimeters per second, so you want to make use of that speed. You want to drive up that tank with full maximum speed. You don't want to stop at any change in wall thickness or at any coupling variations, make new adjustments, change your gauge, change your gain. This is automatically done with this system as you drive up. What we've noticed is that what we know is that the system is fully compliant with both API 653 and EMU 159 inspections. So if you are inspecting according to these regulations, then Scorpion is definitely a product that you could use. We're looking at wall distribution, wall changes, distributions, not so much spot checks, right? We want to see a trend in that data. Very fast inspections, like I said, we can do 25 meter or 82 feet in under 3 minutes. Well, try that with rope access or scaffold building, or, you know, and even then, you know, you have data which is superior to anything that you can get with another product. It can be used on the shell, but it can also obviously be used on tank roofs. Then what you would get is not spot checks, but you would get a real profile of the full tank as you drive up. So this is your crawler, it's driving up this scan line, and as it drives up, you get this scan profile for your measurements. Then we're creating quite a bit of data. So what we want to do is we want to make sure that we can create efficient reporting from that data. So what we've developed is an Excel macro. That Excel macro is actually being able to digest that tank information in sections. So you can say, okay, give me a minimum and a maximum in every 250 millimeters of reading, or 10 inches of readings. It will summarize that and only provide you the minimum and the maximum and its location. Being able to print out a report, as you can see it on this example here, immediately with very little effort to be taken. Let me give you a bit of an overview of the product. So I'm going to switch my view here a little bit. You can see my camera quite a bit bigger. And what I'll do is I'll actually grab a Scorpion here for you. So what we have here is a Scorpion. As you can see, we have 4 magnetic wheels. Battery compartment, we have 2 encoders. One encoder is actually for encoding the values, the measurement values as we go up. The other encoder is also used for compensation for steering, to make sure that we're driving in a straight line. This is the probe head, like I said, and it's very simple to detach that probe. We have these 2 pull levers on each side, and if we pull that lever, we can quickly disconnect that probe head in a matter of minutes, which is quite good because it will actually help us to do maintenance on the probe head quite easily. And there we go. Probe head is off. We now have full access to the wheel probe for maintenance, for cleaning. These are wear shoes that we can take off quite quickly. And for reconnecting it, we just have to create the plugs. Another nice feature is that we've developed a calibration block. The calibration block can be just clicked to the probe head. We can move the calibration block to where we want to calibrate, and make sure that those tracking gates are actually working over the full wall thickness that we have for a tank. So quite convenient. Yeah, great product. A lot of satisfied customers around the world. So what I also want to do now is show you a product video, actually. So what I'm going to do is I'm going to switch my view here, and I'm going to actually change my screen. And there I have a little video on how this product is used in the field. Like I said, it's API and EMUA compliant. Main applications is storage tanks, but we've also seen being used on larger diameter piping, but also on vessels. This is a storage tank farm as we know it. Many of those things are inspected maybe every 10-15 years, and you can do this now with this product quite quickly. Here seeing one of my colleagues, driving this Scorpion up a tank. You can see it moves relatively quick, and as we drive up, we're actually making a measurement every millimeter and recording that data. The probe head can be lifted. If we lift it, it's quite easy to actually do the calibration with the little calibration unit that we have. Swift UT has its own batteries. It has 2 batteries which are hot swappable. So you can actually use one battery, charge the other one, and the batteries charge faster than they run out. So you basically have a complete working day of data or power with this unit. Like I said, Swift, nice touchscreen, very rugged, IP65, so you can use it outside in light rain as well. It has a touchscreen. You can see here the B scans being presented and the A scans. Measurement is actually quite simple, very easy to set up, very easy to deploy, and very easy to demobilize this product as well. So that was a quick overview again on the Scorpion 2. I have another quite nice example for you, which I wanna show you. This is more about the RMS system and using phase array, right? So we have this system designed for measuring tank shells, vessels. And we see a lot of use of this product currently for measuring all sorts of degradation mechanisms on vessels. Again, if we look at vessels, then there's a number of things that can attack the integrity. One of the bigger problems at the moment are HTHA and HIC. And a lot of customers really want to see if their vessels and their heat exchangers are still safe to operate. So this product is actually great for using that. It can detect a number of things like HTHA and HIC, like I said before, but also microbiological corrosion, stress corrosion, interface level corrosion, delamination, lining, and cladding issues, for instance. If we look at the system, then it's an inspection raster scanner. So what we saw with the Scorpion, it was just one straight scan line that we're creating. Here we're actually scanning a complete raster and mapping out a whole area on a vessel of a tank. We're using a phased array with a conventional probe, 64 elements. We have a 1x1 millimeter resolution. And if you compare this to normal scanning with a single probe, it's probably about 10 times faster at a very high resolution data of 1x1. We have a detachable scanning head. So the scanning head at the front here is detachable, which can also be used as a manual mapping system. Which one I will show you later as well. And if you have the right configuration with a Gecko or a Mantis, you could actually also use TFM. For enhanced defect characterization. So specifically, if you want to find stepwise cracking with HTSA and HIC, this is definitely a technology TFM to look for. Only currently available with the combination as we have it with RMS and Mantis or Gecko. Then a system like this basically has 4 different systems in one. We have a single probe scanning system which can be attached. We have the option to scan with phased array. We also have a manual unit and a fully equipped phased array unit. So you get 4 products in one if you use a system like this. What I would like to show you is an example of a project that we've done. And let me take a sip of my coffee here. I would like to give you an example of a project we've done with some quite nice results using phased array scanning on a vessel with a nominal thickness of 18 to 22 millimeters, 0.7 to 0.86 inches. We use linear phased array. We use an aqualock system, so we use water as the coupling. That was a 15 millimeter aqualock that we have on this unit as a default configuration. We have other heights for water locks as well. Using a 1x1 configuration pitch with a 64 element probe and an appendager of 8 with a 7.5 megahertz. And the whole scan of this tank bottom, not whole, but the section that we could reach, we've done 7 scans in 2 hours. So that's quite productive for a unit. And doing this by hand, you would get less good data, and obviously probably take you quite a bit longer. And also the reporting would be quite a bit more difficult. So this is the layout. This is the vessel. We were scanning at the 6 o'clock position that you can see in the blue areas here. So we create a nice cat layout, and then when we're done making the measurements, we stitched all that data together to be displayed on the vessel. This is actually one of the defects we found, so quite good data, quite good results here on this defect. You could see that what we're showing here is a C scan together with an A scan, a B scan, and a side view. And the color scale that we can actually change that to change the severity of showing these defects. And what we can also see here is the internal weldment. So there's probably like a plate being welded on the inside, maybe for a stiffener, maybe to separate the vessel into heat zones. Not sure. But we can see them clearly on the UT data as well. So what we found is that the nominal thickness was 18 millimeters, 0.7 of an inch. And we actually measured the minimum wall thickness to be 10.38 millimeters or 0.4 inches. Quite great results. This is immediately very valuable data for the asset owner, and I think great data for a service company to present to his customer. Another vessel we've done was a vertical vessel, quite thick, 140 millimeters thick, 5.5 inches. Again, we used a linear phased array probe, 1x1 millimeter resolution, 46 element with an appendager of 8 and a 7.5 megahertz probe. Again, we've done the layout, the cat layout, where we actually showed the data being taken, and the walkway was only this section here, so we actually had to measure outside the reach, the normal reach of a human to do the measurement. Basically, the RMS crawler can be remotely controlled and driven by a joystick or by the controls on the Gecko or the Mantis. So if the measurement would have been taken anywhere else on this vessel, also would not have been a problem, because we can remotely maneuver the unit there and start making those measurements. So I have 2 sets of data here. So one set of data is the UT time of flight data. The other one is the amplitude data. Again, we've created a cached layout and stitched all that data together to give it a nice overview. I think this consists in a total of about 12 different scans. And we immediately identify a big area of corrosion actually on this portion here. And what we also see is that the amplitude data here is actually changing. So not only the UT data is of value, but also the amplitude data, because in this area, the internal reflector, the back wall, would actually also be deteriorating already, not really showing as a defect, but will show on amplitude data in the end. Here we have a bit of a zoom in on the one of the scans. We can actually see the data, see the defect. Again, we have a color scale showing the severity, which we can obviously change within either the gecko or the mantis. Nominal wall thickness 140 millimeters, as we said, 5.5 inches, and we measured the minimum wall thickness here to be 136.4 millimeters. So quite a few millimeters lost. We don't know if this is critical. This is for the asset owner to actually determine that in the end. But also a nice comparison here is that if we go back, then if we look at the UT data, there's basically nothing to be shown here, but we can see it here on the time of flight data. So I've compared put both the time of flight data and UT data into one scan to give you an example. Is that this is the time of flight data where we can see the defect, but also the amplitude data can sometimes give us information on, for instance, where are internal weldments, stiffeners, or whatever is there on the internal surface, which can be nicely seen on the amplitude data. And again, I have a nice product show for you to show for you. This is the front head. I don't have a full RMS scanner in my office. Obviously, also my office is not very suited for a wet environment. So I'm just showing you this probe head. So in this probe head here, we have the manual version. This is the front, which is on the front of the RMS phased array unit. It can be detached again with 2 pins being released. We have 4 wheels encoded. Wheels are magnetic, so they'll stick to the surface automatically. On the top, we have 2 buttons, one start stop and one index button. So we don't have to do all the controls on the gecko or the mantis. This is actually the connector for the encoder. We have the feed for the water supply and the connector for the phased array probe. Here in the bottom we can see the cavity for the water. This is a little sponge, actually making sure that we adhere to the surface, and the sponge will make sure that we don't lose too much water or don't use too many water as we measure going up. And you can see the Equalock inside being clamped. It's quite easy to take it off. We can release these 2 pins, take the unit out for cleaning or changing or whatever, maybe another frequency probe or whatever you want to do. The nice thing about the water by using a water column is that we can track, specifically with the new version of Capture 3.1, we can actually track the reference gate for the water level, and we can now see that gate change. We can also use synchronization of gates, so we can get quite smooth back walls for when we stitch all those individual scans together as one complete scan. Recent release, but we have a lot of demand for this product at the moment. So let me switch back to the video that I have for you on this product. Actually showing you the measurement in progress with this for this project. So these are the vessels. That's the RMS actually on the vertical vessel. You can see that it's outside of reach. We're using the controls of the RMS or the controls on the gecko to actually do this. Data was taken at Oleum in Dunkirk in France. Thank you, Oleum, for this opportunity to do this, and Sprint Robotics. Here we can see the scanner move from one position to the other. It's quite simple to actually change position with the controls, either the joystick. This is the example on the horizontal vessel. You can see actually the mantis and the control box situated on the floor. We only have 3 components, so it's not too bad. And as you do the scanning, you can actually see the live data of the C-scan on the screen. Very simple setup in the few stages that we know with Gecko or Mantis, where we set up the object, the probe, and the phased array settings. The unit can move quite quickly as well. Like I said, it's about 10 times faster than what we see with traditional single probe scanning. So a lot of benefits here on using this application. So let me switch back to my presentation where I have one final project that I would like to show you, which is a robotic inspection of internal conditions of pipelines, but then long lengths of pipelines. So in this case, we needed a crawler, a robot, which could travel over a large distance, up to 1,000 meters. And we needed to combine this robotic capabilities with UT. So what we've done here is we've actually combined the R-scan. I have this R-scan in my office, which I'll show you in a minute as well. Driving up a pipe, and this R-scan is now attached to the robot, making measurement as it goes. So the idea is here that we on a pipe which could be a nominal wall thickness from 5 up to 22 millimeters, so about 0.19 inches up to 0.86 inches of wall thickness. Measurements taken every 10 millimeters or 32 feet intervals, where we do coordinal points like 12, 3, 6, and 9 o'clock positions, and create small B scans, as we saw similar approaches with the Scorpion, but then internal to a pipe. And those B scan lengths would be up to 20 to 30 centimeters in length. But the pipe length is up to 1,000 meters. So we need to be able to travel this unit up 1,000 meters of a pipe, and then still be able to measure the pipe wall thickness, create small B scans, and collect that data while we're viewing it 1,000 meters away. So a special, project and a product, and it shows the capability of Eddyfi combining our Inuktun robot sets together with our UT capabilities. Of course, you could do this, but maybe like eddy current ACFM, shark probe, spine probe. There's a lot of combinations possible. So we do this bespoke projects as well with pleasure, I must say. Again, let me show you a little bit on the product here. So this was the probe that we connected to the robot. It basically has the same wheel probe as the Scorpion 2. Touches the surface. There's a little a container in the back containing a little bit of oil, and we're oiling that probe as we drive along. It's a spring-loaded probe, so it always attaches to the server, and it makes B scans as we drive it along. Also, the great addition to the Scorpion 2, we sell this as a separate handheld product. So if you want to measure like small diameter piping, something within reach, we have a nice pole that you can extend on longer lengths as well, to make B scan measurements on something like this as well. So to close out, I have a final video that I would like to show you. And I will switch to that video now. Quite nice example, and a nice video created by my good colleague Liam. There we go. Let's look at this. So what we see here is a nice shot of the robot, obviously used for internal scanning of piping. Here we can see, we're feeding the umbilical through. This is a shorter umbilical, and now we see the maneuvering of the probe head, so we can basically rotate that head and move that in any position to create that B scan or measure that coordinal point that we want to measure. Of course, all being remotely controlled up to 1,000 meter. Data being fed back to a data acquisition unit as we know it. Could be a Swift UT, but obviously it could also be done with other products, other technologies, and maybe a Ready or maybe a Gecko. So a lot of combinations are possible. Of course, it takes a bit of work to actually put this together. But all in all, a great and successful project moving ahead. Here you can see the UT data being sent back to the unit from inside the pipe. Here we can see the travel through the pipe. Again, the rotation of that probe head, being able to control it on any location inside the pipe. This is a control unit which is outside of the pipe, of course, controlling the whole thing from quite a bit of a distance. We can see again the B scans being collected. You could quite nicely see the floating gates adapt to the variations in coupling variations, and you can see the probe actually making a measurement. Okay, so that was the end of this video and my presentation. I hope to kept it brief enough and interesting enough for you. I hope that you have further questions, so please allow me to invite you to ask those questions in the chat. I should be able to see them soon. So, and also, if you are interested in more videos like this, more NDT videos, please subscribe to our channel on YouTube. And I would also like to tell you that we have another coffee break session tomorrow with my good colleague Laurent Lebert. He will be talking about the Penter and phased array TFM and a new application which is called plane wave imaging. So if there's any questions, then please let me know. Okay, I'm trying to connect to the feed for the questions. So a question come in. Is it possible to put more than one R scan on a robot? Yes, of course that is possible. It would we require some changes in the mechanics. What we're also doing for this project, for instance, is we're adding a brush. A brush that will go ahead of the probe and actually clean the surface for creating optimal optimal surface conditions for the probe. But yes, definitely we can create that. So few more questions coming in. So for phased array and about the maximum surface temperature, I think we have to separate two things. If we look at the RMS phased array system, then the temperature is limited to 100 degrees Celsius because of the maximum temperature of the phased array probe. If you, however, want to measure a vessel which is much higher temperature, say up to 200 degrees Celsius, then you could also use a single probe. So we can work up to 200 degrees Celsius. And forgive me, I don't actually know what this is in Fahrenheit, but it will allow you to do that with a single probe configuration. The maximum length of the umbilical for the RMS phased array, the maximum length is 30 meters, which is, what's that, 100 feet? But we have shorter umbilicals as well. So if you only need like 7.5 or 50 meters, we also have 7.5 and 50 millimeters umbilicals for the RMS phased array. And the thickness range of a Scorpion 2 is basically 3.5 millimeters up to 100 millimeters. The 3.5 millimeters is in an optimal condition if you have a good back reflector. If it's severe corrosion, it's probably a little bit less. But this is any limitation that you would have with normal UT as well. Okay, so yeah, 200 degrees Celsius is 392 Fahrenheit, and I agree that's very impressive. Okay, I don't see any more. Okay, so the water supply for the RMS system. We basically have a special water supply. It's a 5.7 liter a minute, quite heavy industrial pump, which can easily pump water up to 50 meters in height. And we need this pump because we have quite a big cavity to fill with the phased array. And obviously it's designed for this purpose. So yeah, we have a specially designed pump for that. The Scorpion tool, is it only working with the Swift? Yes. Thank you, Theo, for this question. The Scorpion is actually only working with the Swift, and I can also tell you why. Inside the Swift, we have the motor controls for the Scorpion, and there's quite a bit of intelligence in that Scorpion as well. So, like I said, we have compensation for drift. Um, and that compensation for drift is being calculated and communicated forwards and back with the control unit. Obviously, we also have a joystick on the Swift, which allows it to steer. So without that, it would be difficult to actually control. But yeah, it's the probe head is just a normal UT connection, but it unfortunately works only with a Scorpion 2, or I should say, fortunately. Um, Thank you, Eric. Can the crawler be used underwater with the Arscam probe? No, the Arscam probe cannot be used underwater. The Arscam probe is actually this probe. I consider you we talk about this probe. Of course, we have the UT connections on the inside, and we have the encoder. So it will not be possible to use that underwater. Okay, I'm not quite sure if that were the latest questions or the last questions. If any more questions, then please let me know. Also, you'll see my email address on the sheet here. So if related to the presentation, the technology, or anything else with regards to NDT, I could help you with, please send me an email or give me a call, and we'll be sure to help you. So I see another question from Jean-Francois. What's the maximum surface temperature for the RMS? I think I already addressed that. The maximum surface temperature is basically limited by the phased array probe. It's 100 degrees Celsius. But the RMS with a single probe could actually work up to 200 degrees Celsius. So even for vessels which are still in production, right, up to 200 degrees Celsius, we can still do mapping, high resolution mapping, if you want to. Okay, guys, if this is it, then I want to thank you for watching this. Be sure to watch your hands, keep your distance, stay safe, stay home, and hope to talk to you soon. Bye bye.